All right. So last time we left off, we were going to watch some videos. They weren't working. We'll do that again. We'll watch them again. But first, well, maybe we should watch some videos first. Who votes for videos first? Who votes for first? All right. So it's good to, I think, see the concepts, to visualize the concepts before we go through all the math for them. So let's do that. Let's dive right in. And we will see if these now work. I got to take my AirPods out.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end. The wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, let's try higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is the wave that's set down and reflects.
We're going to have equations.
Constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down. Here it's moving up and down. And we'll see that in a second with a high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node. This is a node, and the middle is a node. We have three nodes to this wave. Now, like I said, second harmonic. Well, what's the first one? The first one will be half this number, so 8.5. And there we go. This is a scenario of a jump. Now, I can find any of the other harmonics are multiples of this number. So we just saw two times this number with the second harmonic, the second possibility. Well, if I go three times this number, I should get the third harmonic. Well, three times 8.5, I guess that was around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's one and a half. One half wavelengths. And it's easier to see in high speed. So check out this shot with a high-speed camera and verify for yourself that it is one and one half wavelengths.
Okay. That was that. That was with the string going up and down. We are going to be dealing with voltages going up and down on a transmission line. Now, we've talked about water a lot, water waves. We've talked about, if you and someone else are creating waves in a pool, you're both creating them, they'll interfere with each other and create standing waves. So here's an example of what that can look like.
Have you ever noticed your phone doesn't charge as fast as it used to? You're not imagining it. Big cell phone manufacturers.
So that's what it looks like in water. Okay, and then we have the real one, which is the closest to our world now with voltages. So he's gonna go through this. I might stop it occasionally. He's gonna get to this point here, which is still graphics of this. And what he's gonna show is that the yellow one is like an incident wave, and he's got a blue one, it's like a reflected wave. And he adds them, because remember, our total voltage is the sum of the incident wave and the reflected wave. And that is this red one. Okay. What we're going to calculate, just always keep in mind, just like with the string, how the string was still going up and down, but at some places there were peaks, and at some places were what he called nodes, right? So we're going to calculate the envelope, and envelope just means like the extreme, like the edges, like the overall amplitudes or the overall magnitudes of the wave. Okay, so for instance, if you had some kind of a sine wave that started off small and then got big and then got small, the envelope would be like if you connected the dots of all the maximas. Okay, that's what we're going to calculate. Okay? So I'll let this go. And this is our last video. This one's about, it's about 10 minutes long or so.
In today's video, we're going to talk about kind of visualizing RF standing waves that can occur on a transmission line when it's not properly terminated in the line's characteristic impedance. We've dealt with terminations and things in the past with a couple of videos, and I'll link some of those below. We also did a video on a directional coupler, such as this one here, that can be used to measure the both forward and reflected waves on a transmission line, and to show that when the line is properly terminated, there's no reflected power, and when it's improperly terminated, you get some energy flowing back the same way. And in our discussions, we've talked about the fact that when you've got these forward waves and the reflected waves coming back, that they'll add up both constructively and destructively in the line, creating what's called a standing wave. So in this video, again, we just want to try and take a look and see how they're formed and what they look like. Now, the Wikipedia page on standing wave ratio has got a couple of pretty good graphics here that show how a standing wave is formed from an incident wave and a reflected wave, and also shows what that standing wave looks like for different amounts of reflection. So I'd encourage you to follow this link. It'll be in the show notes below as well to augment what we're going to show here on the bench today. I'm generating a pair of signals out of my function generator back here to kind of simulate what's going on the transmission line. So let's picture that this wave that's showing going here from left to right is the incident wave coming from some RF source down this transmission line to a load connected at this end. And if the load is a perfect match to the transmission line impedance, there'll be no reflected wave. Now, of course, if the load is either an open or a short, the reflected wave will be equal in magnitude to the incident wave, which we can simulate by adding the second channel here. So I've got the incident wave coming in this direction, getting reflected back, and that's the blue waveform going back the other way. So this is kind of simulating in ultra slow motion here what's going on with waves with either an open or a short mistermination at the end of the line. You can almost imagine that what we see on the screen is kind of a picture of what's going on over a section of the transmission line. Okay. So if the transmission line was perfectly terminated, we'd have no reflected signal, and we'd have a situation that looks like this. The signal at any place across this line, if we measured its amplitude or its power, would simply be the sum of those two signals. So we could turn on a math channel that adds those together, and we can see the math channel, which is red, just overlays right on top of channel 1. And if we wanted to measure the magnitude of that, if we did that with an RMS power meter or a RF detector probe, we just simply measure a constant amplitude. And we can see that just by simply doing a little bit of persistence on the screen. And let's set that to infinite persistence, so we can see we've got a constant envelope of that signal. So pretty easy to understand. So let's take a look at what happens when we misterminate the line. I'll turn the persistence back off, and let me turn the math off here for a second, and let's put on a perfect reflection, meaning either an open or a short, so that the signal is reflected at full amplitude. So now I've got these two signals coming back, and you can kind of almost see that they add up right on top of each other. That's going to create a peak, and then when they're exactly 180 degrees out of phase, that's going to create a minimum. If we turn that math trace back on, we can actually see that happening. So we can actually see now that the sum of that incident wave and the reflected wave are resulting in a waveform that's essentially standing still. Now, what are we going to measure if we tried to measure power, at that, on the line here? Well, again, it helps to put the persistence on here. So let's make an infinite persistence. And we can actually see that the sum of those things creates this beat pattern, actually, that has got nulls, or what we call nodes, at every half wavelength. And then we've got peaks or antinodes at the other half wavelengths. So the amount of power that we'd measure, if we measured power at different points on the line, would be different depending on where we measured it because of that standing wave. Now, it might be a little bit harder to visualize is what happens if the reflected waveform is not at the same magnitude as the incident waveform. So I'll simulate that by turning the amplitude down on my reflected waveform. I'm going to get down to about half of what the incident waveform is. And what happens when we sum these together? If we turn that math trace on, we can see we still get a sine wave, but it's kind of bouncing and moving a little bit, and so it's kind of hard to see what would happen with the standing wave. But again, if we turn infinite persistence on, it becomes kind of easier to see. So we see we still get nodes, if you will, every half wavelength, and peaks every half wavelength. And essentially it's,
We are very short. We're going to go through some math that will allow us to calculate this envelope, find out where the maximas are, find out where the minimas are, come up with something called the standing wave ratio, which is what's the peak divided by what's the minimum. Okay. So just like this, the wave's going up and down, the wave's moving, but this is like this x-axis here, if you want to think about it, is like the transmission line. Okay, so it's pretty much like that. So if you went and you measured it right there, you would never get a voltage higher than that point, right? It's going up and down, whatever, it's moving, but it will never go above that point. But if you measured it right there, the voltage will go all the way up to that point. In other words, your voltage on the transmission line depends on where you are on the transmission line. The current on the transmission line, same thing. So now you've got the weird situation where, depending on where you are on the transmission line, depending on where you measure it, the voltage can change and the current can change from one point to another. Just a little foreshadowing here, what's coming probably Monday. What's impedance? The ratio of voltage to current, right? It's V equals IR. That means, depending on where you look on the transmission line, the impedance changes. So this can lead to weird stuff. Weird stuff like, I'm going to leave it open circuited. I'm not going to connect anything to the end of it. If I come back a certain distance, a quarter of a wavelength, and I look towards that, let's say it's a, did I say short circuit on the end? let's say it's a short circuit, and I go back a quarter of a wavelength, and I look towards the short circuit, doesn't look like a short circuit, it actually looks like an open circuit. It would be indistinguishable from an open circuit, even though it's actually a short circuit. Very kind of weird and non-intuitive stuff, all because incident wave, reflected wave, they interfere with each other. Depending on where you are on the line, the interference is different, which means the voltage is different and the current's different. So the impedance is different at different points on the line. This is only if you have a reflection though. If you don't have a reflection, then you don't have that reflected wave, and you just had that first case where it all filled in red and it was just flat the whole way. Okay.
We go from that kind of half wave rectified thing to something that's a little bit softer, but we still have a standing wave. In fact, the voltage standing wave ratio that you hear about is really a measure of the forward waveform amplitude and the reflected waveform amplitude. What we're seeing here.
So that's
is
not
essentially
right what he just said. I know what he meant. He meant to say the right thing, but what we said earlier was the right thing. It's not that he said something like it's the forward wave amplitude and the reflected wave amplitude. It's the peak of the combination of those two divided by the minimum of the combination of those two. So what we're going to call Vmax and Vmin.
Some of those two things and how you actually wind up getting a standing wave out of that. So in order to visualize the standing wave on an actual transmission line, I'm using this kind of open line here, a strip line. It's about 4 inches long. So we can actually measure the voltage at different points on that line. Now, in order to see a standing wave, we've got to consider the wavelength of the RF signal that I've got coming from the RF source here. In a strip line like this, the speed of propagation is about 6 inches or a little over 15 centimeters per nanosecond. So we have to consider the period of our RF signal, and to ensure that we at least get a half or more than one period or so contained within that strip line. So I'm using actually a 2.5 gigahertz, actually a 2.4 gigahertz RF signal coming from over here. And on this transmission line will give me a overall wavelength of about 2.5 inches, which is, about, that big or so on this transmission line here. So we should be able to see, a couple of nodes and antinodes in the standing wave. But to take a look at the RF voltage that we have on the line, what I'm going to use is this little RF detector probe. I did a video on this as well, just a couple of germanium diodes and a couple of capacitors to detect the RF power. So we'll be able to probe at different spots along the line and actually visualize that standing wave. And I'll start off by putting a 50 ohm termination on the end of the line.
Predictions. What's going to happen? You just put a 50 ohm termination on the end of the line. Probe it. That probe he's got. And that probe is like the probe is like an envelope detector, right? It's just going to do the envelope. And so he's going to try it at different points on the transmission line with that 50 ohm load connected to it. What do you think he's going to see? First of all, what's the reflection? I guess is the first question. If you're talking about the reflection, you should think about the reflection coefficient. What's the symbol for the reflection coefficient? Capital gamma. Hit me with an equation for the reflection coefficient. Yes, that's the one I remember. That's the one ZL minus Z naught over ZL plus Z naught. That's the one you're going to put numbers into and actually use to calculate stuff. The other formula is V0 minus over V0 plus, and that's more of a definition one. You're not going to use that one so much to actually plug numbers into. ZL minus Z naught over ZL plus Z naught. What's Z naught for this strip line, this little board with the transmission line on it? Did he say what Z naught was?
He put on a 50 although he didn't say what the other thing was.
Let's see if he did. I'm not sure myself.
standing wave on an actual transmission line. I'm using this kind of open line here, a strip line. It's about 4 inches long. So we can actually measure the voltage at different points on that line. Now, in order to see a standing wave, we've got to consider the wavelength of the RF signal that I've got coming from the RF source here. In a strip line like this, the speed of propagation is about 6 inches or a little over 15 centimeters per nanosecond. So we have to consider the period of our RF signal, and to ensure that we at least get a half or more than one period or so contained within that strip line. So I'm using actually a 2.5 gigahertz, actually a 2.4 gigahertz RF signal coming from over here. And on this transmission line will give me a overall wavelength of about 2.5 inches, which is, about, that big or so on this transmission line here. So we should be able to see, a couple of nodes and antinodes in the standing wave. But to take a look at the RF volt.
Yep, he didn't say it. Remember how I told you before that in this world, almost everything's 50 ohms? So I had just assumed it was 50 and he had just assumed it's 50 and it was never said, right?
See what happens when you assume.
So it's so often 50, everything's 50, that it almost goes without saying, but I will always say it in any, exam questions or midterms, that sort of thing. So I'm now telling you that Z naught equals 50 ohms. And
So
he's
that's default.
yes, you won't need to assume anything. It should always tell you, but in the industry, it's like, it's everywhere. So I'm now telling you Z naught equals 50, and he's putting a 50 ohm load on there. So what is the reflection coefficient? ZL minus Z naught over ZL plus Z naught. So the numerator is ZL minus Z naught. ZL is the 50 ohm termination, that's the load. And Z naught is the characteristic impedance, which I'm telling you is 50 ohms. So you have 50 minus 50, 0. The reflection coefficient is 0. That means there is no reflection. V0 minus, which is the amplitude of the reverse, the reflected wave, equals gamma times V0 plus, the incident wave amplitude. Gamma equals 0, no reflection.
So
Okay.
if there's no reflection, that's a good thing then, right?
Generally, that's what we want. So now what do you think this is going to look like?
Can be smaller.
So let's go one at a time. Go ahead.
The red wave is going to be smaller because it's not the sun anymore.
Okay, so we've got to vote. And how does it change across the extent of the transmission line here?
It'll just go forward, right? Because
Yes. It's not going to be a standing wave. It will not be a standing wave. It'll be constant. It will be less than the peaks of when the constructive interference happened between the forward and reflected wave. It'll be the same amplitude as just the incident wave.
That we have on the line, what I'm going to use is this little RF detector probe. I did a video on this as well, just a couple of germanium diodes and a couple of capacitors to detect the RF power. So we'll be able to probe at different spots along the line and actually visualize that standing wave. Now we'll start off by putting a 50 ohm termination on the end of the line. And let's probe the voltage on the line. I got the scope going at a very slow sweep speed, so we can actually see the trend as we take a look at this. If I put the probe on here, you can kind of see, the RF amplitude here. It's about 1 division. I'm not going to care about the actual voltage here. There's just about 1 division or so on the screen. And if I work my way down to different spots on the line, you can kind of see that it's about the same voltage no matter where I measure it. In fact, if I very carefully slide this down the line, I get both contacts on there and slide it down the line. Right. You can see there's a little bit of variation here. There's a little bit of a standing wave, and that's because this termination is probably not perfect at 2.5 gigahertz. Me probing it introduces a discontinuity, which is going to add some reflections, and this line is probably not perfectly 50 ohms. So I think it's certainly acceptable that you're going to see a little bit of a standing wave. Okay, not a tremendous amount, but a little bit as we slide this down the line. And we can actually see that as we trace it out. Of course, things would get a whole lot more dramatic if we remove the termination here and leave it as an open circuit. We're going to get kind of that perfect termination or perfect reflection off of that open circuit. And we should see a pretty strong standing wave here. So if I stick the probe onto the line at this end here, see at that point I see very little RF energy. If I slide down the line here, you see the RF power coming up. So right about here on the line, we're sitting, pretty close to, max power, a whole lot higher than I saw before. Let's slide down the line a little bit further. You can see the voltage coming down. Right about here, it reaches a minimum. There's one of our nodes. We go another half a wavelength further down the line, my RF power comes back up again. Okay, so you can actually see that standing wave. In fact, if I try to move this linearly at a constant speed, we should be able to trace out that standing wave pattern. Let's see if I can do that. I'm going to try this one more time to see if I can get a nice clean picture of that standing wave pattern. All right, here we go. There we go. That's a pretty clean picture. I scooted along pretty at a constant speed here, and I can actually see that standing wave pattern that looks just like the envelope of what we saw on the Wikipedia page, as well as in the RF measurements that we did earlier on the scope. And I hope you enjoyed this short little video on visualizing RF standing waves on misterminated transmission lines.
So, any questions about that? All right, let's make sure that, okay, looks good. Apologies to Emerson and Jan. I don't think they could hear or maybe even see any of that. You may also find that on the recording, at least when I did it with the other section, it's supposed to be recording everything on my screen, but it did not record any of the YouTube. Oh, good, Emerson heard it, great. I don't know if it's a piracy thing or whatever, but hopefully it works on this one. If it doesn't, no big deal. You already saw it and it's got the link there. You can just watch it, right? Okay, so that's that. That's kind of the visualization, trying to see what it is that we're doing. And now I got to go through all the ugly math. All right. Why? Well, the big takeaway from all that is the voltage is different at different points in the transmission line, the total voltage. You saw how extreme it can get. It can go to like, there's no voltage at this point, to there's a voltage at this other point nearby that's actually twice as big as the initial voltage amplitude was. And it could be anywhere in between. And as I said, the current also changes, which means the impedance changes. So you need to know it. Like if you were designing something, like someone else designed something, and then you're designing something to connect to it, and then someone else is designing something that's going to connect to your thing, and they're connected up with transmission lines, and you don't really know what's going on. You didn't pay attention to any of this stuff. I mean, it's very possible not, you have to know what to make things work, is the bottom line, right? You have to know what the impedances are and what the characteristics are and that sort of thing. Normally, the way things are done is that everyone designs their, circuit or their subsystem so that it has a very low reflection coefficient. So that like their input impedance is 50 ohms to whatever their circuit is. So you just abstract that away and just say, well, that's like a 50 ohm load. And you design all your stuff with that 50 ohm load. And then when that second system gets connected to yours, as long as the input impedance does look like 50 ohms, everything's fine. Okay, so let's go back to the math. We did that example. Okay, here we are. So let's do it. So this is our friend here. We've seen this for a while now. It's actually a slightly simplified version because we are dealing with lossless lines only for this part of it. And where that comes into play is because when we had this equation before, it didn't look quite like that. We had a gamma in there, right? We had not the big gamma. The big gamma is reflection coefficient. The little gamma, the alpha plus J beta, the propagation constant. if we're lossless, so we had this alpha plus j beta, but alpha equals 0 for lossless. So alpha's gone, so we could just substitute in the j beta. So that's where that came from. Okay, so this is our slightly simplified version. Then we have the equations that I recommend that you memorize or that you have on your prominently on your formula sheet for gamma. This tells you the symbol. It's a reflection coefficient. It tells you the definition, which is the V0 minus over V0 plus. What's the amplitude of the reflected wave? Divided by the amplitude of the incident wave. And then it tells you the equation that you're going to use to actually calculate this thing. ZL minus Z0 over ZL plus Z0. Also, if you just brought that guy over there, you just multiply it, both sides by V0 plus, right? You get that. This allows you to know, it's another way to think about it, the amplitude of the reflected wave is the gamma times the amplitude of the incident wave. This is why if gamma equals 0, there is no reflected wave. And then this equation here would tell you when would gamma equal 0? If the numerator of ZL and Z0 were equal to each other, right? That's the matched load. Well, what could we do here? We have a V0 minus there. So what if we plugged that into there? That's no big deal, right? I mean, we would just have gamma V0 plus, right? And then we'd have a V0 plus there, and we'd also have a V0 plus there from that V0 plus. We'd have V0 pluses in both of them. You can factor out that V0 plus. That's what we got there. So we got V0 plus times e to the minus j beta z, V0 plus times e to the minus j beta z, V0 minus, which is gamma times V0 plus to the e j beta z. This is the form we're going to use most of the time from now on. So we don't explicitly write it in terms of V0 minus, we only write it in terms of V0 plus and the gamma. All right.
Professor?
Here's where, yes, go ahead.
I don't know if you were writing on the screen just because I'm not able to see it on Zoom right now.
Oh, really? Oh, okay, hang on. Sorry, I'm not crazy talking to myself, just. Okay, it stopped the broadcast for some reason. How about now? Is it good?
Yeah, all good now. All good now.
Thanks for letting me know. All right. So now we want to calculate that envelope that I kept talking about. That we want to calculate the envelope because the envelope tells us the extremes. Like at this point on the line, it'll never get bigger than this. And it won't get smaller than that, right? We know the range of how much constructive interference we're going to have and kind of what's our worst case destructive interference, okay? So we want to calculate it. How are we going to calculate it? We want to calculate the magnitude of the voltage, right? Because all those are magnitudes. The envelope is the overall magnitude. And when we were talking about envelope, we're really talking about the magnitude of the voltage at different points on the transmission line. So we got to calculate the magnitude of V at Z. Yeah. So that came out quite a ways back. And so you can look back at exactly where it came in. I can kind of tell you that came in. It's a good question though, because it's a little bit non-intuitive why that's there. That came in all the way back from our solution to the wave equation. So all the way back there, you can look back and basically, really that goes back even further to when we calculated our like when we did our Kirchhoff's voltage and current laws. But it's a good question because that is kind of a funny thing, right? But they should be different because they're going to have different behaviors. We'll see shortly when the voltage is at a peak, the current's at a minimum. And so there is this kind of phase shift between them. Okay, calculating magnitude. How do you calculate magnitude? Well, the way you commonly calculate magnitude is if you had a complex number and it was in rectangular form, you would do like the real part squared plus the imaginary part squared, and then you take the square root of it, right? That's like converting from rectangular form to polar form, and in the polar form, the magnitude's out front. That's one way that you can calculate the magnitude of a complex number. Another way that's also fundamental and equivalent is to take the number. So if we wanted the magnitude, what we want is the magnitude of v at z, like that, okay? So to get it, you can take v at z and multiply it by v at z complex conjugate and take the square root of it. If you want to be convinced of this, let's say you don't buy it. You're like, no, I don't buy it. You can take a complex number, just pick one, 3 plus j5 or something, right? Calculate the magnitude of it using the way I just talked about, where you could say the real part squared plus the imaginary part squared. So it'd be like 3 squared plus 5 squared, take the square root of it, you get a number. And then try calculating it this way. So this would be your 3 plus j5. You'd multiply that by this one. That would be 3 minus j5, because complex conjugate, you flip the sign of the imaginary part. Then you take the square root of it. You get the same thing. So the way that we're going to calculate the magnitude of v at z is like this. Now, this first part, we're in pretty good shape, right? Like, we're going to use this. We've already got it. We already wrote it out. Okay, there's only one small thing we're going to do first. We are just going to remember that gamma has a magnitude and a phase. So gamma is a complex number, has a real part and an imaginary part. Anytime you have a complex number, you can write it as a real plus j imaginary, or you can write it in polar form as magnitude with some angle. Now, with some angle, you could write it as, that's perfectly fine. So if you don't like the e to the j stuff, it's just whatever the angle is. How do you get the angle? Well, if it's a complex number, you do the imaginary part divided by the real part, inverse tangent. That's the angle, okay? So we can plug that into there. So like that one can go into there. And so we would just explicitly write magnitude of gamma times e to the j theta r. So theta r, don't forget about your theta r. It's an easy one to forget about what that one is, where it comes from. You get asked a question to calculate the reflection coefficient and you forget about the theta r. So remember the theta r. The r is for reflection coefficient, okay? So if we did that, then we're good on the first part. Our v tilde at z, we just have v0 plus e to the minus j beta z plus magnitude of gamma e to the j theta r times e to the j beta z. Okay, that's this. So this whole thing here, so this part is gamma, and this whole thing is v at z. This whole thing is v at z complex conjugate. So let's talk about where that one comes from. So when you want to do a complex conjugate of something, pretty much you flip the signs, right? You flip the signs of the imaginary part or of the angle. So the first part, so basically we just want to do the complex conjugate of this, right? So the first part is the v0 plus. Well, it's kind of like, all right, I just wrote the complex conjugate sign. We don't know what it is. We could have broke it out and wrote it kind of like this, where we have magnitude of v0 plus e to the j some theta for v0 plus. But we're going to have an easy simplification here in a second. So that just says whatever v0 plus is, it's a complex conjugate of it. All right, negative j beta z, complex conjugate, goes to positive. Magnitudes don't change in complex conjugation. It's just the angles or the imaginary part. Exactly. Wherever you have a J, you change it. Positive to negative, positive to negative. Okay. All right. Now, look at our definition here that we're using of magnitude. The magnitude of something is the thing times the complex conjugate of the thing, square root. The thing times the complex conjugate of the thing, square root. So that can come out front as the magnitude of V0 plus. Okay. You're not going to have to repeat this derivation here, but it's good to understand where it comes from. Okay. Especially if you're reading the book and it'll just say like, you know, that equals, you know, that or that, and it won't necessarily talk about the steps in between. Sometimes it's good, and sometimes it skips some. So that, because each of this whole thing is going to get multiplied by this whole thing, which really means that is multiplied by this, and that half means square root means that. So that's where that comes from. That's why we left it in that form. And now we can kind of forget about that because it's out front. Okay, now we've only got the stuff in the parentheses, all the E stuff, right? So what do? Well, this one's going to multiply by that one's going to multiply by that one by that one, that one by that one. Just like regular multiplication, right? You got two terms and you're multiplying it by another two terms, and so you just have to multiply each thing. So first one, that one times that one. What does that equal? E to the minus j beta z times e to the j beta z. E to the 0. Because they have the same base, right? They're both exponential. And so you add the minus j beta z plus j beta z, it adds to 0. You have e to the 0. E to the 0, it's 1. That's where that one comes from. Okay. So we kind of described that one. That's where the 1 comes from. E to the minus j beta z times e to the j beta z. We'll do them a bit out of order here. Yeah. So what would that one be? The second and fourth, the magnitude gamma e to the j blah, blah, blah. Magnitude gamma e to the minus j blah, blah, blah. So I think you missed the magnitude gamma in there though, right? Because there's magnitude gamma, and then all of these are going to add up to e to the 0, but then there's another magnitude gamma there. Magnitude gamma squared. That's where that one comes from. Okay. All right, last one. This is where like that one's by that one and that one's by that one. So let's look at the positive ones just to avoid the negatives, okay? So this one times that one. Well, e to the j beta z, e to the j beta z. So we're gonna have magnitude gamma, e to the j theta r, e to the j2 beta z. So magnitude of gamma e to the j 2 beta z plus theta r. So that's where that one comes from that multiplication. This one's the same, we just need the negative sign. Okay, now let's call that x, and we'll call that is the same thing. So that's x. So basically what we're saying is x equals 2 beta z plus theta r. And then we could say, well, e to the jx, well, that's just our Euler's formula, right? So that's going to be cos x plus j sine x. And e to the minus jx, well, that would be cos x minus j sine x. And so what we really have here is e to the jx plus e to the minus jx. What will that equal? Yeah. These ones go away. We're adding them together, right? So we have cos x plus cos x. We have 2 cos x. Where x 2 cos, where x is 2 beta z plus theta r. Okay, the magnitude gamma came through, the 2 came from here, and we have the cos 2 beta z. And now we're out of phasors. We're out of phasors, we're out of complex exponentials. We just have kind of a regular expression here. Let's just do one more thing before we look at it some more. Do you remember where we defined z to be equal to 0? At the load. Because it made our life easier, because we're often worried about what's happening at the load. So we just define z equals 0 to be at the load. But we can't change the direction of z, because kind of everything we've done has been assuming that z increases from the source to the load. That meant we had to go to negatives. Like if your line is L long, the source then is at minus L, so that by the time you get to the load, you get up to 0. But then we introduced last time, we said sometimes we're going to use this d, where d equals minus z. Just to flip the sign, just so we don't have to deal with negatives. It doesn't really matter, right? It's just to get rid of some negatives. So if we wrote this, let's just say that part, because that's the only part with a z in it, right? So that would turn into cos minus 2 beta d plus theta r. Now, cos is an even function. So like if I pick a number, when I said punch into your calculator, cos of 257, and then you did the cos of minus 257, it's the same thing. So in other words, the cos of x equals the cos of minus x. You can multiply the junk inside the parentheses by -1 and get the same thing. So if we multiplied this by -1 inside the parentheses, we get that. This is the form we're going to look at it here. I just wanted to kind of lay out, you're not going to have to go through and do this derivation, right? But I want you to kind of know where things come from. So now we're going to have this exact expression, but written in terms of the d. So you're going to have the 2 beta d minus theta r. 2 beta d minus theta r. Okay, we finally got there. And you see this blue curve? Think the envelope of that red wave when he turned on the infinite persistence. Okay. So let's talk about it. Like, what does this thing mean? Always good. This is in general. Check your axes before you try to figure out what's going on in a graph. What's your y? What's your x? Okay. X is d. Okay. Then think to yourself, okay, where is 0? Okay, so this is 0 here. What is 0? What does d equals 0 mean? Where are you on the transmission line? You're at the load, because we said z equals 0 is the load. D equals minus z, minus 0 is 0. So over here, you are at the load. As you go this way, so it's like, this is the load right here. As you go this way, you're going towards the source. You're going away from the load a certain distance. Y-axis, we're in volts. This is the magnitude of the voltage at different positions on the transmission line. And as we saw, the magnitude of the voltage is different at different points on the transmission line. Okay, so this is for a specific numerical example here. So here's the specific example. Z naught is 50 ohms. Gamma equals 0.3 e to the j30. So what's the magnitude of gamma? 0.3. And how would you kind of visualize that, or like, what would you kind of think in your head about what that means in terms of how much is reflected? What's that? Yeah, about 30% of whatever you send down 1 volt amplitude. Well, 0.3 times 1 volt 300 millivolts, that's the amplitude of the reflected wave. Okay, so just by looking at that part alone, that's magnitude of gamma. If it's something really small, that means you have a really small reflection, which is going to cause less interference overall. If it's close to 1, that means almost everything is getting reflected. That is theta R. So theta R, 30 degrees. So don't neglect your theta R. You can see why this is the most important thing usually, right? Because that's telling you how much gets reflected. Yeah, so that's the thing where you're often kind of predominantly interested in that, which is why the theta R can sometimes get thrown under the bus and forgotten about, okay? Okay, this 0.3 e to the j 30 is that. So let's see if we can convince ourselves how it's that. This equation with gamma equal this gives the blue line. So V0 plus magnitude, that's the magnitude of the incident wave. We're not going to change that in like the middle of what we're doing. So we can just consider that one to be fixed. It's said it's 1 volt or whatever. I think that's what it is in this case. It's 1 volt. So we're not changing it. It's 1 volt, period. Okay. Magnitude of gamma. Well, that's 0.3. We already said that, right? And you can say, well, is that kind of varying? Like, does that vary with like our position or something like that? And then you can think, well, what is gamma? Gamma, I've just been calling the reflection coefficient, but really technically it's the reflection coefficient at the load. Because where that equation came from was right when we decided, let's let z equal 0 at the load. Because then all the complex exponentials were e to the zeros and everything got a lot easier. But the way we calculate it is ZL minus Z naught over ZL plus Z naught. So ZL is the load impedance. We're not like changing the load impedance in the middle of this. Like the load impedance is fixed for a scenario, just like V0 plus is fixed. And Z naught is the characteristic impedance. We're not changing that either. That's, you know, based on the R prime, L prime, G prime, C prime. So it's fixed as well. So what I'm getting at here is that's not changing. Like, remember, our x-axis is D here. So V0 plus doesn't depend on D. That's just the magnitude of the incident wave. Gamma doesn't depend on D because that gamma is the load reflection coefficient. That's how this was all derived. Doesn't change, doesn't change. Theta R is just the angle of the reflection coefficient, doesn't change either, okay? Because that just comes from ZL minus Z naught over ZL plus Z naught. So all we're really left with in this whole equation is beta and D. All right, so let's look at beta. Someone hit me with an equation for beta. The wavelength divided by, okay, that is one. There are a number of equations here. I like the one that you were going with, the 2 pi over lambda. Not that the other ones are wrong. I just find this one easy to look at here. Yeah.
You said due to the change, that everything else is the same except for the beta and the delta, right?
Maybe. I haven't discussed them yet, but carry on. Yeah.
Well, I was thinking, if you're only focused at one point,
Yep.
interest,
Yep.
then D will have.
Right. And maybe, let's see if it changes. So beta, one of our equations for, this is like the first beta equation we saw was 2 pi over lambda. We've gotten a number of other ones since, and you could do the same thing with those. Let's take this one, 2 pi over lambda. 2 pi is 2 pi, that's a number. 2 times 3.1415962, whatever, right? So it's really just lambda. So someone hit me with an equation for lambda. 1 over f is the period.
Yeah, I'm thinking the velocity over frequency.
Yes. So in terms of our symbols, UP divided by F, okay? F it's known, it's always known. I don't think there'll ever be a case where you don't know F. And the reason is, if you were working in industry or something, the clock is right now. If you're working in industry or something like that, you're going to be designing a project. If you're designing this Wi-Fi base station here and you're designing the circuits in it, you know it's going to have to operate at 2.45 gigahertz and 5.8 gigahertz, right? You're designing a radar system, you know what frequency it needs to operate at. So we basically always know F. So you can pretty much go like, I know that one. Okay. What about UP? Yep. So what's an equation that we could use? So I've stopped saying it in the titles, but everything here is assuming that it's lossless. Why? Because where did this come from? You can often just, and it's a useful learning exercise as well to trace it back. So let's say you had this equation, you're like, is this for lossless or is this not? Is this a general case, like losses could be included? Because this is going to be an ongoing thing where you're going to have a pile of equations. Which ones apply generally? Which ones apply to only lossless? So we would trace this one back and we'd go, well, where did this come from? Where that equation came from here, which came from here, and all the way back to, well, this is V at Z, and we didn't have an alpha in it. We didn't have a gamma in it. If it was including losses, alpha wouldn't equal 0, and we couldn't just have a J beta Z. We would need to have the alpha included as well. So all of this stuff is for losses. Can anyone think of an easy formula that I think we talked about the last class for UP that only applies in the lossless case? Yes. So simplest equation for UP, C divided by the square root of epsilon R, but only applies if it's lossless. So now I could tell you, yeah. So now you're designing a circuit for your, the iPhone 17 or something, and it needs to work at a bunch of bands, but the one that you're interested in is 1 gigahertz. Okay, so F is 1 gigahertz. All right. All right, so that tells you the denominator of the lambda. The numerator UP, well, that's going to depend on the epsilon R. So then I tell you, you're designing it on a printed circuit board. It's got a pretty high epsilon R. The value is 9. Okay, so what's UP? Yep, which is 1 times 10 to the 8. C is 3 times 10 to the 8. If epsilon R is 9, square root of 9 is 3. 3 times 10 to the 8 divided by 3, 1 times 10 to the 8. Okay, so now we've got UP. 1 times 10 to the 8. F is 1 gigahertz. That's 1 times 10 to the 9. 1 times 10 to the 8 divided by 1 times 10 to the 9. Lambda is 0.1. Lambda is always in meters. It's a wave length. Okay, so 10 centimeters, I don't know, something like that, right? Okay, now we got UP. So we have lambda, so we have beta. So we know that number, okay? So all that's left is D, the distance from the load. So basically what I said, and all of that was, you know the rest of the stuff. Okay, that's all that was saying. Normally, if you're doing a design, you know everything else. And if you're only interested in one point on the line, then you can just plug in that value of D and you're good. If you want to see how it changes across D, then you could change D, starting at 0 and then increasing, going back to the source. So let's see how this plot came about. So let's find what the maximum is. Let's find V max. How do we do it? Well, we just plug the numbers in here. We got to look at this though. What's the biggest that can be? Cos of whatever can only be 1. Cos just goes between +1 and -1, right? So we don't know exactly what the value of D where that happens is, or what these values are necessarily that causes that, but we know the biggest that can be is 1, And this whole thing is being added to, right? Doesn't change, doesn't change, doesn't change, doesn't change, doesn't change, does change. Biggest it can be is 1. So the biggest the whole thing can be is when that equals 1. So let's assume that's our case. So we'd have 1. So we can kind of forget about that because it's 1 times something. 1 plus magnitude of gamma squared. So it's 1 plus 0.3 squared plus 2 times 0.3. This is times 1, right? You get some number. Don't forget though, we got to take the square root of it. If you punch that into your calculator, you would get a value of 1.3. That is the maximum. That is Vmax. If you want to figure out, well, what's Vmin? What's the lowest it can be? You'd say, well, what's the lowest that can be? Because it's the only thing that changes. So what's the lowest that coast can be? Yeah. So you would do 1 plus 0.3 squared plus 2 times 0.3 times minus 1. You'd take the square root and it would equal 0.7. So it equals 0.7. Everywhere in between, you want to connect those dots. You could go into MATLAB, plug in all those numbers, and let D be an array. D equals 0, colon, 0.1, colon, 10 or whatever it goes up to. Plot it all and trace it out. Okay, so we got our Vmax and our Vmin. Later on, we're going to figure out, well, where does the max occur and where does the min occur? We have something called the standing wave ratio, which I've already mentioned, and they mentioned it in the video as well. It's just Vmax divided by Vmin. So our Vmax that we just calculated when that cos equaled 1 was 1.3, and the minimum it can be is 0.7. So we have a 1.86 standing wave ratio. Now this standing wave ratio has a bunch of names. It is as common, maybe more common than the reflection coefficient in industry. If you buy pretty much any RF or microwave component and you look up the data sheet, they'll either give you the standing wave ratio or the gamma. So to give you an idea of what does 1.86 mean? Is that good? Is that horrible? Is that like what? So let's say if you were working for a company, like let's say you're working for Lockheed Martin or something like that, and you're designing some radar system, and you need an antenna for it, then you got 2 options, right? And companies always have to make these kind of decisions. Do we design an antenna or do we buy an antenna from another company? And to answer that question, it's normally, does such an antenna exist that meets our requirements, that meets our needs, that operates at that frequency, is the right size, has the performance we need, is not too expensive, right? Based on that, you might find one and great, we'll just use it. It'll save time, save trouble. They've already designed it. Or you'll go, no, the thing we need does not exist. And so then you would look to the antenna design team and they would design a custom antenna for your application. Let's say you're looking around, you're going to try to buy one. So you'd go to some antenna companies, there's lots of them. You'd look up their data sheets to try to find out, does this antenna meet my requirements for this application, for this radar system, right? And on that data sheet, almost without fail, they will give S. They won't call it S though. They may call it the standing wave ratio. Most likely they'd call it SWR for standing wave ratio. It's called the standing wave ratio. It's called SWR. It's really the voltage standing wave ratio, or the VSWR. And people also call it the VISWR. And we're also giving it the letter S. So that's kind of like 6 different ways you're referring to the same thing, okay? Think about what it means. The maximum divided by the minimum. So what would S be, the standing wave ratio be, if it was perfectly matched? It would be 1, because if it was perfectly matched, That means ZL equals Z naught. So gamma, ZL minus Z naught over ZL plus Z naught, gamma equals 0. If gamma equals 0, gamma, well, V0 minus the reflected wave amplitude is gamma times V0 plus. Gamma equals 0. There is no reflection. If there's no reflection, there's no interference. There's no wave like this at all. It's a flat line like we saw when he hooked up the matched load. If it's a flat line, the maximum and the minimum are the same point. There's no variation. And so you have one number divided by the same number. It equals 1. What do you think the worst case or the biggest S could be? We haven't defined it fully yet. We're going to talk about this more next class. I'm just wondering if anyone. So not quite. We're going to have a formula for S in terms of gamma shortly. I would think about it this way, and it's a little difficult to tell at this point because we haven't looked at it enough. But Vmin, maybe you could tell from that video when he had the open circuit on, Vmin can go to 0. Well, Vmax is not 0. So it can go up to infinity. It can go up to any number, okay? Could you have a standing wave ratio less than 1? Which doesn't make sense, right? So you can't, because otherwise your Vmin would be your Vmax. And so it doesn't make sense. You can't have a standing wave ratio less than 1. So between 1 and infinity. And to go back to that example, if you're looking for that antenna and you look up the data sheet, they're definitely going to have the voltage standing wave ratio. And there's really like 2 numbers that everyone goes by. Close. For a standing wave ratio, almost everyone defines a like a working antenna or like an adequate antenna as when the standing wave ratio is either less than 2 or less than 3. Just how it is. That's just how everyone says it. If you're an antenna designer, and you're designing an antenna, one of your design goals is to make the VSWR definitely less than 3, hopefully less than 2. Okay. And all of that just goes back to Vmax divided by Vmin, which all goes back to what gamma is from the interference between the incident wave and the reflected wave. How are we doing here? We got 4 minutes left. Okay, so this is kind of a summary here. The maximum value occurs when the waves are in phase. Now, I didn't really talk about when that occurs. I just said the biggest cos can be is 1, right? Okay, the underlined red part. What does that have to equal to make cos equal to 1? What's that? Let's just think about a number. If you were just to plug in numbers, what would the total 2 beta d minus theta r be to make the cos of that a 1? 0, 2 pi, 4 pi, 6 pi, 8 pi, right? It repeats itself because cos is just starts out at 1 and then repeats itself every 2 pi. So the maximum is 2n pi, where n can start at 0. Could be 1, could be 2, could be 3. Okay. When that's the case, the cos equals 1, and we're at a maximum. Okay. The minimum, then you'd have to think, well, we said the minimum occurred when the cos was equal to -1. So then you just have to say, cos of what equals -1? The cos of pi, right? It starts out at 1, cos starts out at 1, goes all the way down to -1 in the middle. It ends back up at +1. So right in the middle is 180 degrees, or pi. But of course, it repeats itself every 2 pi as well. And so we just have to offset it like that. Like n equals 0, well, then 2 times 0, that's gone. 1 times pi, we just have pi. So the thing in the parentheses, the argument of the cosine, when it equals pi, then it's -1. And then this business, just if n equals 1, It's 2 times 1 plus 1 is 3 pi, right? Pi, 3 pi, 5 pi, 7 pi, and so on. If we're matched, we have no reflected wave. And this last point here, just remember that we're dealing with the envelope. Everything's still oscillating really quickly with time. Like our frequencies are like 1 billion cycles per second. You saw the string still going up and down, right? We're just interested in its extremes. How high can it ever possibly go? Or how low can it go? And I think that's probably, we'll end here because we've already seen this. It's kind of a review. Match line, we have a flat line, right? Short-circuited line, we have this type of pattern. What we saw in the video was the bottom one. So we'll pick up here on Monday. We have now pretty much, with the exception of like one little thing, we've covered everything in the last quiz. Okay, so we'll just, you can pretty much do it all now. The only last thing is just this equation. There's just 2 equations that we're just about to talk about where they come from. And then I think you're able to do that entire quiz. So Monday, we'll finish that up and the next quiz will be launched then as well. Okay. All right. So have a good weekend and I will see you on Monday.